So when you're involved in a startup, what are some of the things that you have to think about? Okay, and this is stuff you will learn on your own as you're working in industry. But what what are the some of the things that you need to concentrate on so that you're up with where people are at? In other words, how do you what do you do first, second, third? Well, first of all, you find where the fast food places are in the city where you're working, and it may not be your hometown, it may be someplace else, but wherever it is, you need to find where they are because usually you're too busy to have long meals. But you need to find where the fast food places are. Not that you're always going to eat fast food, but basically you're going to have to do that some. We always used to have to go find the Radio Shack because we would buy the alligator clips that you needed for your jumpers, and they don't have those anymore. So you have to take the jumpers with you so that you have the alligator clips in your suitcase or whatever. But you definitely need a supply of 20 to 40 alligator clips. So I'm going to list those. And then you arrive at the site, wherever that is, and you go in and introduce yourself at the construction trailer. And then the first thing you're going to do is you're going to say, obviously, where's my set of prints, and kind of look and see where the bathrooms are and all that kind of stuff. But you need to find your prints because usually a set of your prints are on site. And you might have a set with you, but you need to find where their set is. Have they marked things up already? Have they done something to the prints? That type of thing. And then you're going to ask, basically, you're not going to ask, you're just going to say, I'm going to go out and look at the motors, and I'm going to inspect all the motors. Okay? And you're looking at the faceplate or the of the motor, and you're going to get the full load amps, FLA, and you're going to make a list of FLA for your motors. Now, much to your surprise, maybe not to your surprise, the plan of the motor that was on the drawing originally and the actual motor may not be the same. Okay? So you may end up with a 25 instead of a 20, or a 15 instead of a 12, or a 12 instead of a 15. It can vary. And in that case, what do? You go back and complain to the people that say, no, I have a 15 on my drawing, and you've got to change that motor out to a 15. No, you have to match the breaker and the overloads to the actual what's out in the field. So that's your first. And what does this do for you? It gets you out of the trailer and it makes you look competent. Okay? You may not have a clue the first day about what's going on, but after you've gone all over the whole site and looked at every motor and looked at all the nameplates, not faceplates, the nameplates, Ted. If you've looked at all the nameplates and inspected them and looked at them for all the peculiarities of the motors, you have started to become accepted as part of the construction team. It takes a day to do this, okay? So it gives you a day of buffer where people are looking at you and say, well, you're the new person, you don't know anything, and they're going to test you. But if you go out and you look at the motors and find, what you're going to find is you're going to find everything. When you're finding the motors, you're going to find where the panels are, the state of the panels, what the electricians are doing. They're sizing you up because they want to control they want to control, and you're in control. You're the person that's got to start up the system. So you're in control, but you have to establish your control, okay? So that's why you have to do things the first and the second day to establish yourself. You can't just say, now, where's that panel? No, that's not the right thing you say. You go out and you inspect the motors, and in the process of inspecting the motors, you eyeball everything. Does that make sense? It gives you something to do. It gives you an activity before anybody else can ascertain what you are or can't do. And it gives you credibility, because that has to be done. That's the first thing that has to be done on a job site, is to find the stupid motors. And are they the same motors that you planned for? And are they where they're supposed to be? Are they wired? Are they not wired? All that kind of stuff. But basically what you're looking for is, do I have the right size breaker, and do I have the right size overloads? Or do I have to go back? Now today, most overloads are settable in the field, and you can actually set them. The older style overloads, they were already to a certain value, and you had to match them. So you had some extra ones in your, someplace you had a bunch of extra ones, but the overloads had to match exactly the motor overload current that you wanted, okay? So if the motor overload, if the full load amps was 20, you would want to go with 21.5 or something like that. You want to go a little bit above, but not much above what their rating is. So that's what you need. And that's simple, but yet very profound. You have to go a little bit above, but not by much. That's your overload settings, and you have to get those, or it won't run, okay? Now, the motor might not be wired yet. You want to inspect to see if it's wired and all that kind of stuff, but that's where you're at. So I want to go back and I want to look. I'm going to cheat a little bit today. I'm going to do a Pytel nameplate one, and then a Pytel Megger one, okay? So we're going to do this one at a time. They're not long, and we'll get you out of here. So basically, I want to do those two. And I'm not always going to do Pytel, but daggone it, today we're going to do some of those, okay? So let's do Pytel. Nameplate, YouTube video. Well, actually, there's two of them.
1 spoonful of honey with cinnamon before bed equals 0 memory collapse. The secret, the $1 billion...
Good day and welcome to Big Bad Tech. I'm Instructor Jim Pytel. Today's topic of discussion is motor nameplates. Our objective is to learn to read and interpret pertinent manufacturer, electrical, and mechanical information displayed on a motor nameplate. This lecture operates under the assumption that viewers watch the Motor Family Tree lecture, available at the Big Bad Tech channel, as a passing familiarity with three-phase AC electrical power and rotating mechanical power calculation and measurement. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. As you are no doubt aware, the Motor Family Tree is a gnarled and expansive beast with numerous branches containing many different varieties of motors, each with their own peculiar natures and performance characteristics. This lecture primarily deals with three-phase AC squirrel cage induction motor nameplates for the simple reason that three-phase AC squirrel cage induction motors are the most popular rotating electrical actuator of choice for industrial applications. Additionally, a majority, but not all, of the entries in a three-phase AC squirrel cage induction motor nameplate are common to a number of other motors. As we introduce different types of motors in later lectures, I'll make sure to highlight important performance differences we encounter. For now, consider this lecture a general primer on the subject. A motor nameplate is a mini data sheet affixed to a motor in question describing its most important characteristics at the rated condition. In the event a motor is damaged, one can order an exact replacement or, lacking an exact match, interpret the motor nameplate entries to find a comparable replacement from a different manufacturer. In a perfect world, all manufacturers would utilize a common template, thereby enabling readability and interchangeability, but they don't, and it is the wild, wild west, and absolutely anything and everything goes. This being said, most manufacturers have enough sense to include the most important information, even though it might or might not appear in the same location. There's a bunch of different information on motor nameplates, but I like to classify each piece of data as belonging in one of three different informal categories: manufacturer information, electrical characteristics, and mechanical characteristics. Some motor nameplates also feature additional optional information. This lecture will restrict itself to discussing the most common and important entries. Before we do, let me make one point absolutely clear. A motor nameplate is not a data sheet. It is a mini data sheet for one single point inside a motor's larger operational range. This point is known as the rated condition. At the rated condition, the motor produces its rated mechanical power, rated torque, and rotates at its rated speed. The motor nameplate is a snapshot of those properties one might expect to observe at or around the rated condition. At the rated condition, a motor might be expected to draw the rated current at a specified power factor and operate with a specified efficiency. Operated at anything other than the rated condition, in excess or below the specified point, a majority of the entries on a motor nameplate are subject to change. For example, if an induction motor is excessively overloaded, we might expect its speed to decrease, current to increase, and efficiency to decrease, among other effects. Data at other than the rated condition is customarily not found in the motor nameplate, but rather it can be found in the motor's associated data sheet. A motor's complete data sheet will specify properties for a range of operating conditions, customarily on one or more charts. We'll examine motor data sheets and properties at other than the rated condition in later lectures. Again, the rated condition is a single point inside a larger operational range. The entries in a motor nameplate assume this rated condition. What's nice about this fact is customarily motors are operated at or around the rated condition because that is what the motor has been specifically designed to do. Why would you regularly overload a cheaper 3/4 horsepower motor with a larger 1 horsepower task? The 3/4 horsepower motor won't be as efficient and most likely won't survive repeated use. Why would you ever underload a larger 5 horsepower motor with a smaller 1 horsepower task? The oversized motor is more expensive, heavier, and most likely won't be as efficient. If you've got a 1 horsepower task, buy a 1 horsepower motor. At or near the rated condition, everything in the motor nameplate should be reasonably accurate, and if it isn't, something is wrong. In this sense, motor nameplates make handy troubleshooting cheat sheets. Let's take a look at the manufacturer information category first. Manufacturer, model, and serial number. This basic information is comparable to the make, model, and VIN number of a car. The manufacturer is the company that made the motor. The model number, or sometimes catalog number, is specific to that manufacturer. It means only something to them and not any other manufacturer of similar motors. The model number is that manufacturer's means of coding that specific style of motor, and it is also useful for finding replacement parts for that specific style of motor from that specific manufacturer. The serial number, if it appears, is a unique identifier for that particular motor. Ideally, a manufacturer would be able to look up that serial number using their historical database and tell you when and where it was manufactured, whether it is or isn't under warranty, or whether that production run this particular motor was part of has any known faults or issues. Like, let's say, an annoying tendency to burst into uncontrollable flames. Here's an example motor nameplate. Looks like this model W0881709 motor was made by Hampton, and this particular motor's serial number is
Watch what magnesium does to your bowels.
If you have to wipe more than 4 times after you poop, here
530-75185. The next category on a motor nameplate pertains to the electrical aspects of the motor in question. The most important of these entries specify phase, frequency, voltage, current, power factor, efficiency, inrush code, and connection diagrams. Phase. The phase entry specifies if the motor in question is intended for use in an industrial 3-phase AC environment or a residential single-phase AC system. Compare and contrast these two 1 horsepower motor nameplates. Even though these are both 1 horsepower motors that run at the same speed, they are not equally applicable because this 1 horsepower motor necessitates 3-phase AC, whereas this 1 horsepower motor necessitates single-phase AC. Frequency. The frequency entry specifies the excitation frequency the motor in question is intended to operate with, ordinarily 60 Hz in the US and 50 Hz in the EU. All entries in the motor nameplate are specified at this particular excitation frequency.
And Canada.
As we learned in the rotating magnetic field lecture, available at the Big Bad Tech channel, synchronous speed, the speed of the stator rotating magnetic field, is directly dependent upon excitation frequency. Motors operated at a higher frequency rotate faster, whereas motors operated at a lower frequency rotate slower. Related to this fact, some motors can be used in both 50 Hz and 60 Hz systems. If so, a manufacturer often splits the entries on a motor nameplate to specify properties at 50 Hz and again at 60 Hz. Here's an example of one such motor. This nameplate is a column specifying properties at 60 Hz and again at 50 Hz. As one might expect, the rotational speed at 60 Hz is faster than when operated at 50 Hz. Voltage. This entry specifies at what voltage the motor is intended to operate, allowing for a 10% tolerance. For three-phase AC motors, this is the larger line-to-line voltage, and it is not the smaller line-to-neutral voltage. For example, consider a motor intended to operate with a light industrial three-phase AC system characterized by 120-volt line-to-neutral and 208-volt line-to-line. This motor would be specified as suitable for 208 volts, regardless if that motor is configured in a Y or delta. Again, the voltage specified on the motor nameplate is always the three-phase AC larger line-to-line voltage. The 10% tolerance stems from a NEMA requirement that a motor deliver its rated horsepower at plus or minus 10% of the nameplate voltage. For example, consider a motor with a nameplate voltage of 200 volts. Allowing for the 10% tolerance, this motor should be able to deliver the desired mechanical output for systems down to 180 volts or up to 220 volts. This motor would therefore be suitable for a light industrial three-phase AC system characterized by 120-volt line-to-neutral and 208 volts line-to-line. The slightly lower nameplate voltage value of 200 volts ensures the motor has enough punch when it's hooked up to the higher nominal system voltage of 208 volts. Oftentimes, a motor nameplate includes two entries in the voltage field. If so, this means this motor is a dual voltage motor. And pending proper use of the connection diagram, which we'll examine later, the motor can be wired for either low voltage configuration or high voltage configuration. Dual voltage motors allow for a degree of flexibility for different electrical distribution systems.
If you eat butter daily, this is what happens. The reason butter is called butter is...
Here's an example of a 2-horsepower motor with a dual voltage rating. When windings are wired in parallel for a low voltage configuration, this motor can run at 208 volts up to 230 volts with a 10% tolerance. If, however, the windings are wired in series for a high voltage configuration, this motor can run at 460 volts with a 10% tolerance. Current. The current entry on a motor nameplate specifies the amount of current drawn per phase when the motor is operated at the rated condition. As with the voltage entry, dual voltage motors often have two entries in the current field, one for the low voltage configuration and another for the high voltage configuration. In our previous example, this 2-horsepower motor draws 6.5 amps per phase, while in the 208-volt low voltage configuration, 6.2 amps in the 230-volt low voltage configuration, and only 3.1 amps per phase, while in the high voltage 460-volt configuration. We'll discuss electrical power in a moment. However, it should be noted that the lower voltage configurations draw more current, whereas the higher voltage configuration draws less. Given power is voltage times current, this should make sense. Lower voltage with higher current yields the same power, as does higher voltage with lower current. Again, I must remind you the current entry in a motor nameplate specifies the amount of current drawn by the motor when the motor is operated at the rated condition, or to use a similar term, fully loaded. For this reason, rated current is sometimes referred to as full load amperes, or FLA. If the motor is underloaded, we might expect line current to decrease, whereas if the motor is overloaded, we might expect line current to increase. Anything in excess of the rated current would therefore be considered an overload condition. Momentary overloads aren't ordinarily an issue. However, sustained overloads produce excessive heat and may damage the motor insulation over time. It is for this reason motor starters incorporate not only a contactor, the means of making and breaking connection, but also a means of protecting the motor from sustained overload conditions, called an overload relay. We'll discuss motor starters, contactors, and overloads in later lectures. Some motor nameplates include accessory information about current. If a nameplate includes the accessory entry NLA, this is the no load amps, drawn while the motor is free spinning and experiences no oppositional torque. If a nameplate includes the accessory entry LRA, which stands for locked rotary amperes, this is the inrush current drawn when the motor is first started at a standstill or locked rotor condition. Inrush current is many times that of rated current. Thankfully, it's relatively brief. We'll examine the inrush code in a moment, which can be used to calculate inrush current. Power factor. The power factor entry on a motor nameplate is a measurement of how much apparent power in units of volt amperes being delivered to the motor is available for conversion into real output power in units of watts. Power factor is several things. 1, the ratio of real power over apparent power, or 2, the cosine of the phase shift between voltage and current. Motors are inductive loads and current will understandably lag voltage. Three-phase AC motors are customarily considered balanced loads. An electrical power in a balanced three-phase AC system can be calculated as follows. Apparent power S in units of volt amperes is equal to square root 3 times the line-to-line voltage times the line current. Consider the previous motor nameplate. While in the high voltage configuration and experiencing the rated load, this motor draws 3.1 amps at 460 volts. Square root 3 times 460 volts times 3.1 amps yields roughly 2.5 kilovolt amperes of apparent power. Real electrical power in units of watts is equal to apparent power times power factor. This motor nameplate indicates this motor does so at a 0.77 power factor. Roughly 2.5 kilovolt amperes times a power factor of 0.77 demonstrates this motor consumes roughly 1.9 kilowatts of real electrical power input.
These look like regular glasses, but what they do is on another level. Don't risk straining your eyes or wasting money on.
While we've got this example in front of us, let's discuss efficiency. The efficiency entry on a motor nameplate specifies that portion of real electrical power input that is successfully converted into usable mechanical power output. Losses might include heat, friction, noise, among others. This motor nameplate indicates this 2 horsepower motor operates at 82.5% efficiency. 82.5% of roughly 1.9 kilowatts demonstrates the motor yields 1,569 watts, or roughly 1.5 kilowatts of usable mechanical power output. A unit conversion demonstrates roughly 1.5 kilowatts is equivalent to roughly 2.1 horsepower, extremely close to the nominal or nameplate value of 2 horsepower, as one might expect. It's a 2 horsepower motor. As with current, power factor and efficiency entries on a motor nameplate are specified at full load conditions and will vary considerably over the operational range. Overload conditions might be associated with more current, higher power factor, and poorer efficiency. Underload conditions might be associated with less current, lower power factor, and poorer efficiency. Oftentimes, the rated condition is a region of peak efficiency, or nearly so. We'll examine electrical properties of three-phase AC squirrel cage induction motors in greater detail in later lectures. Inrush code, or kilovolt amperes per horsepower code, or just plain code. In the event the motor nameplate doesn't explicitly specify LRA, or lock rotor amperes, this is a letter code which can be used to estimate inrush current experienced upon closure of a full voltage or direct online starter. As I mentioned previously, the initial inrush surge can be several times full load conditions and must be accounted for. Luckily, inrush conditions don't last for long, and once the rotor comes up to a rated speed, current levels out. Each letter in the inrush code refers to a range of constants in a kilovolt amperes per horsepower chart. You can estimate inrush current by using the constant in this calculation, where inrush for a three-phase AC motor is equal to the value of the code times the mechanical power in units of horsepower divided by the rated voltage times 577. If this is a single-phase AC motor, the 577 is replaced by the constant 1000. Notice there's no I, O, or Q code, and it stops at V. It's a trick question if the motor nameplate code features letters that don't appear on this chart. As a rough estimate, most motors experience an inrush of roughly 6 times the rated current. Motors with a kilovolt ampere per horsepower code closer to A experience less, whereas motors with a kilovolt ampere per horsepower code closer to V experience more. We'll revisit inrush calculations and the electrical theory explaining inrush in later lectures, but let's try a simple example. Consider the previous 2 horsepower motor rated for 460 volts in the high voltage configuration with code K. In the high voltage configuration, we know it draws 3.1 amps. If we just wanted a quick estimate about inrush, we could say it's going to draw roughly 6 times 3.1 amps, or roughly 18.6 amps. This is an okay estimate. However, the inrush code can give us a much more accurate result. Code K represents a constant of 8 to 8.99. So same for center of mass, and say it's 8.495. Substituting this value, the mechanical power and horsepower, and the rated voltage into the equation, demonstrates we would expect to see an inrush of 21.3 amps in the high voltage configuration. Again, luckily inrush doesn't last for long, but you've definitely got to take a 21.3 amp surge into account. Connection diagrams. The last electrical property, connection diagrams, are pictorial representations of the wiring configurations for different voltages if the motor is dual voltage, or different speed characteristics in the case of multi-speed consequent pole or multi-speed separate winding motors. This entry in the motor nameplate necessitates another independent lecture since it's pretty important. If you're following the Motors and Generators playlist in its intended sequence, it's most likely the next lecture, and I need you to remain poised in a cat-like state of alertness until then. Long story short, you get 0 points for creativity. Follow the connection diagrams exactly as illustrated, otherwise serious repercussions may result. As we learned in the electromagnetic interaction lecture available at the Big Bad Tech channel, polarity of the magnetic field is dependent upon current direction, and a motor might be damaged, or at the very least not work well if it isn't properly wired. Additionally, as we learned in the rotating magnetic field lecture, also available at the Big Bad Tech channel, swapping any 2 phases in a 3-phase AC system results in a reversal of the rotating magnetic field. Hook up a motor exactly as intended, and it will work as intended. Do anything else, and it won't. Again, the upcoming motor connection diagram lecture deals exclusively with this aspect of the motor nameplate. The next larger group on a motor nameplate pertains to the mechanical aspects of the motor in question. The most important of these entries
Hey, Mom? Where are you off to? Tennessee. You're going...
specify mechanical power, rated speed, design, frame, enclosure, installation class, temperature data, and duty cycle. Mechanical power. The power entry in a motor nameplate is the output mechanical power in units of horsepowers or watt, where 1 horsepower is 746 watts. As we learned in the mechanical power lecture, available at the Big Bad Tech channel, rotating mechanical power is the product of twisting force called torque in units of Newton meter times rotational speed N in units of RPM divided by the constant 9.55. Motors can be sized in one of 2 general classes, fractional and integral. Fractional motors are those motors less than 1 horsepower, like a 1/4 horsepower, a 1/3 horsepower, or a 1/2 horsepower, i.e. fractions of a horsepower. Integral motors, in contrast, are motors greater than 1 horsepower, like 1 horsepower, 2 horsepower, 5 horsepower, etc. A related property, rated speed, is the rotational speed of the shaft in units of RPM at full load conditions. Ordinarily, rated torque is not directly specified in a motor nameplate, but can be back calculated using our understanding of mechanical power, torque, and rotational speed. An algebraic manipulation of the mechanical power formula, solving for unknown torque, demonstrates that torque is equal to the mechanical power times 9.55 divided by rotational speed. Consider the previous 2 horsepower motor with a rated speed of 1725 RPM. A unit conversion demonstrates 2 horsepower is equal to 1,492 watts, or roughly 1.5 kilowatts. Substituting mechanical power in units of watts and rotational speed into our algebraic manipulation demonstrates this motor produces 8.3 Newton meters of torque at the rated condition. Related to mechanical power and rotational speed, the design or design code entry on the motor nameplate specifies the shape of the motor speed torque curve. Design B is the most common, but sometimes you'll see design D motors designed to lift loads with large static inertia. A design B motor could move a load from a dead stop at only slightly higher than its rated torque. However, design D can move a static load at almost 3 times its rated torque. As the shape of these curves imply, design D motors are designed for low-speed, high-torque applications like a crane or a hoist. We'll examine differences between design B and design D motors in greater detail in later lectures. The frame entry on a motor nameplate specifies dimensions of the motor as well as the locations and dimensions of the attachment points used to mount and properly secure the motor. There are NEMA and IEC frame charts available for cross-referencing these dimensions. For example, let's say we need to know the shaft diameter of this particular motor. The motor nameplate specifies as a NEMA 56C frame. The diagram accompanying the NEMA motor chart identifies the shaft diameter as property U. It looks like a frame 56 motor has a shaft diameter of 5/8 of an inch. Enclosure. The enclosure entry in a motor nameplate identifies the level of protection taken to shield not only the motor from the outside environment, but also the outside environment, i.e. operators, for the motor's live electrical connections and rotating parts. Open motors are enclosure types that allow the passage of air through the motor to cool the windings. There are several different types of open motors where each designation specifies the level of protection afforded against the ingress of certain sized particles and from certain angles. Enclosed motors, in contrast, are enclosure types that prevent air from entering a motor. Oftentimes, these types of motors necessitate accessory components or systems to aid in cooling. Insulation class. The class or insulation class entry on the motor nameplate refers to the lifespan of the insulating material given standard operating temperatures. All else being equal, the higher the insulation class letter, the longer it's going to last at higher temperatures. A motor with Class A insulation will last 20,000 hours at 105 degrees Fahrenheit, whereas a motor designed with higher quality Class H insulation is designed to last the same 20,000 hours at 180 degrees Fahrenheit. One can estimate insulation lifespan at other than the standard temperatures using a chart like this. Let's say you got a motor with Class B insulation, and you're operating it not at the standard 130 degrees Fahrenheit, but rather an increased 150 degrees Fahrenheit. If we find the intersection of the sloped B curve with the 150 degree Fahrenheit vertical line and follow it horizontally to the left, we find this motor insulation will last only 9,000 hours. As one might expect, higher operating temperatures shorten the lifespan of a motor's winding insulation. We'll examine a special purpose tool called an insulation tester in later lectures that can quantify a motor insulation integrity. A related entry, inverter or vector duty, if it appears, would designate a motor as being suitable for operation with a motor drive. A motor drive, sometimes called a variable frequency drive or VFD or an inverter, is a power electronics device we'll examine in later lectures that can vary the excitation frequency and voltage magnitude to a motor under its direction, and thus change rotational speed and torque. Motors designed to work with motor drives have upgraded insulation and can remain cool even at reduced operational speeds.
If you've got honey at home, you might be one step away from wiping out your memory problems. Today, I'm going to show you how to make
The ambient temperature entry on a motor nameplate is the maximum allowable temperature of the air surrounding the motor, whereas the temperature rise entry would be the difference between the winding temperature of a running motor and the temperature of the environment. Motors designed to be exposed to direct sun or operated in hot environments include special design considerations. Lastly, the duty cycle entry on a motor nameplate refers to the length of time a motor can be expected to run without being turned off and given a chance to cool. If the motor is designed to operate for unlimited periods without rest, it would be specified as having a continuous duty cycle, whereas if it was designed to run only occasionally, followed by a break, it would be specified as having an intermittent duty cycle. Motors intended for intermittent duty will specify the length of time the motor is allowed to run, typically 5, 15, or 30 minutes of every hour. All right, that about concludes our brief tour of the most important manufacturer, electrical, and mechanical entries on a motor nameplate. As I mentioned previously, not all motor nameplates include all data, nor are they formatted identically. Additionally, motor nameplates may include accessory information, like service factor, which is kind of like a multiplier to a motor's permissible power rating, meaning it can be operated at a degree above the rated value without suffering damage. Electrical characteristics at service factor and or mechanical information like bearings or lubrication might also be printed on a motor nameplate. Despite the variance in forms and entries, you should be able to interpret important manufacturer, electrical, and mechanical entries at the rated conditions for most purposes. We'll examine electrical and mechanical properties at other than the rated conditions in later lectures. In conclusion, this lecture discussed the pertinent manufacturer, electrical, and mechanical information found on a motor nameplate. This information is extremely helpful in finding an equivalent replacement motor during maintenance and repair procedures. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember.
So I've never hardly ever paid any attention to the inrush code, but you should, because that code, if it's not a small one, you might have to increase the size of your breaker or your circuit breaker in front of your motor starter, and that is important. So again, the full load amps, the current is important. Power factor, efficiency, kind of, but the inrush code is important that you actually make some, make that a, something you actually record and make sure that your breaker is big enough to take it. Okay, and those are the things that you really want to do. You may have to climb in order to find these, so that's one of the things that you have to get over is being scared of heights. You have to do that. Sorry to tell you, but somebody's got to do that kind of stuff. And if it's not you, I don't know who it's going to be. But on the other hand, maybe there's a technician or somebody that will go do it for you. I don't know. But you need to know all this information, okay? And I have one more I want you to listen to today, and this is going to be fun. I think, hopefully, I'll be blunt, I haven't listened to this one, but you probably see that so see if he, if this one's,
This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. This lecture features the Megger AVO 835 digital multimeter. The AVO 800 series multimeters are as reliable and accurate as the historical AVO units, but now come with a range of features to meet today's standards of electrical testing. For more information on the AVO 800 series multimeters and other Megger products, please visit us.megger.com. Amps, volts, ohms. AVO. The Megger AVO digital multimeter is the one tool that does it all. The Megger AVO 835 digital multimeter, as the name implies, features multiple test and measurement functions integrated into a single portable package, including, but not limited to, DC and AC voltage and current measurement, resistance, temperature, phase sequence detection, and more. Today, we'll take a brief introductory tour of the Megger AVO 835 and briefly examine the resistance, continuity test, and conductance measurements functions. The AVO 835 features a backlit display, function buttons, a rotating function dial, and selectively accessible terminals based upon the chosen function. To place the Megger AVO 835 into ohm meter mode, rotate the function dial to the selection with the ohm symbol. We'll explore other functions and the function buttons in later lectures. In this position, the AVO 835 allows access to the black common terminal and the red live terminal on the left, identified with an ohm symbol. Black lead into the black hole. Red lead into the red hole. An ohm meter measures the resistance of an element in units of ohms placed between the two tips of the leads. The element under test must be depowered and isolated from the system. In the current configuration, the DMM displays OL, which is shorthand for over limit, indicating the resistance between the two probes is too great to be measured, which implies an open circuit. This is the DMM's way of telling us there is no conductive path between the two probes. When I touch the probes together, resistance plummets, indicating the test leads present an extremely low resistance path. This is an excellent way of function testing the leads. Leads with a break would indicate an open circuit and would not be suitable for testing the resistance of other elements. Now that we're certain we've got a functional set of probes, let's test the resistance of some electrical components. Again, the element under test must be depowered and isolated from the system. Consider a resistor exhibiting the following 4-band color code: yellow, purple, brown, gold. See if you can use your understanding of the 4-band resistor color code to determine the nominal or nameplate resistance value for this resistor. By all means, pause the lecture and try this on your own. If you're tracking, you should obtain the following value. Yellow, purple, brown, gold means 4, 7, followed by 1, 0, meaning this resistor has a nominal or nameplate resistance of 470 ohms, plus or minus 5%, meaning it might actually be between 446.5 ohms and up to 493.5 ohms. Let's use the ohm meter function to test if this resistor is inside its expected tolerance. When placed between the probes of the ohm meter, the nominal 470 ohm resistor appears to have a resistance of 0.4624 kiloohms, or more appropriately, 462.4 ohms. This is inside our expected range. You'll note the Megger AVO 835 is auto-ranging, meaning it automatically picks the most appropriate range to obtain the most precise results. For this particular resistor, with a nominal value of 470 ohms, the AVO 835 has chosen the up to 1 kilo ohm scale. The sliding analog scale points roughly at the middle of the 1 kilo ohm range. The sliding analog scale is a handy feature for quick resistance measurements. Should you deem it necessary, one can also override the auto-ranging feature and manually range the meter by pressing the range function button. A user has the choice of the up to 100 ohms, 1 kilo ohm, 10 kilo ohms, 100 kilo ohms, 1 mega ohm, 10 mega ohm, or 100 mega ohm scale. If you're using the up to 100 kilo ohm scale, the DMM displays 0.45 kilo ohms, whereas at the up to 100 scale, the DMM displays OL, meaning the element of the test is over the limit of the chosen scale. For most routine resistance measurements, normally the meter is kept in auto-ranging mode. Let's now examine the audible continuity test function. On a very basic level, ohm meters are commonly employed to check the continuity of a circuit. Forget measuring resistance in units of ohms. Is something connected or is it not connected? Opens, i.e. items with no conductive path, would be identified with an OL on display. In contrast, items with a conductive path would be identified with a small resistance value on the display. Consider this length of wire. The ohm meter indicates that this wire has an extremely low resistance value, implying it is contiguous with no breaks. Consider, however, this length of wire that's been subjected to some mechanical abuse. Is it still in one piece? Outwardly, it appears no different than our previous wire, and you might initially suspect it's fine. However, the ohm meter reveals a dark secret that this wire is in fact broken inside the insulation, and no conductive path exists from end to end. Ohm meter works for these types of checks. However, there's a better way to perform a continuity test. In addition to the numerical measurement of resistance, the AVO 835 offers an audible continuity test. In summary, if there's a connection, it beeps. If there's no connection, it doesn't beep. On a more sophisticated level, the AVO 835 emits a constant tone if the connection is below 5 ohms, and an intermittent tone for connections between 5 and 50 ohms, and no tone for connections above 50 ohms. To place the AVO 835 into audible continuity test mode, press the yellow mode button in the center while in ohm meter mode. When the probes are separated, the DMM is silent. When I touch the probes together, the DMM produces an audible tone. The audible continuity test mode is pretty handy because you can check continuity of a mess of wires without ever having to glance up and look at the screen and interpret numbers. Let's use the audible continuity tester to check the continuity of a circuit breaker, a type of heavy-duty switch. With the circuit breaker open, the audible continuity tester remains silent. When I close the circuit breaker, the audible continuity tester indicates that continuity exists. The Megger AVO 835 additionally offers a conductance measurement in units of Siemens, where conductance is 1 over resistance, and 1 Siemen is 1 over 1 ohm. To place the AVO 835 into conductance measurement mode, rotate the selector switch to the ohm meter function and press the yellow mode button twice. Consider a series combination of two 10 mega ohm resistors, presenting a series resistance of roughly 20 mega ohms. The conductance of this series circuit in units of Siemens would be 1 over 20 mega ohms, or roughly 50 nanosiemens. The AVO 835 in conductance measurement mode demonstrates this circuit actually has a conductance of roughly 50.7 nanosiemens, extremely close to the theoretical value. Lastly, I must remind you that resistance, continuity, and conductance measurements must be taken on a de-energized circuit. In the event the Megger AVO 835 detects a live circuit, the instrument will sound an audible pulse beep and flash voltage over limit on the display. This audible warning prevents an operator from damaging the instrument, the circuit, or themselves in the case of an errant energized circuit. All right, that's about it for this brief introduction to the Megger AVO 835 digital multimeter and the ohm meter, continuity test, and conductance measurement functions. We'll examine other functions and features of the CMM in later lectures. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.
Okay, so what's different between that and a DMM? Is that just a DMM or is it not? Is that like the lab, like the digital multimeters we have in the lab or not? Is a megger equal to a digital multimeter or not? It's not. The old style meggers, I'll give you a clue, were nothing more than the old telephone ringer that jacked up the voltage to 500 volts. I don't know if these use 500 volts, but the old style did, and they went at 500 volts. Very low current, but it was a very high voltage, and they tested at high voltages so that you would actually see if it was working at high volts. And old style meggers were used, and this is illegal, but they were used for something else in addition to checking to see if a motor, basically these check to see if the motor leads are shorted to the frame or to each other. And they'll test at high voltages. In other words, when you use a DMM, you're checking at the battery voltage, which is the 9 volts that's in the battery, which is not high enough to break down any shorts. 500 is. So 500 volts, if you put 500 volts, it will find any weakness in the wire or any weakness in the insulation, whereas 9 volts won't. That's why they use meggers. A DMM is not the same as a megger. Okay? I don't know how high the voltage is in this guy, but I suspect it's in the 500 volt range. But it's at a higher voltage. That device right there that he was holding is not the same as a DMM. All right? It tested 500 volts. And what else did they used to use the old style crank meggers for besides checking the wiring of a motor? Fishing. Yep.
Wires in the water.
Yeah, you put one in the water. Here's your canoe. And there's the side of the canoe. You put one on the side of the canoe and you put one out in the water. And everything in between that, you got 500 volts going between here and here. And anything in that area will come up to the surface. All you got to do is dip it out with a fish net. I never did that. But that's a cheesy way of fishing. It's not a, you follow me? Everything between the two will come up. And they won't be dead. They'll wish they were dead because they were getting 500 volts going through them, but they're not dead. They're still very much flopping around. But I never did it, but I certainly heard about it. And anyway, so now you know a little bit about meggers, you know a little bit about full load amps, and you got some idea about what you got to check when you go in a startup, right? The startups sound like fun. No? They have it's a team, and at the end of a startup, you always have a party, and it's kind of like any kind of a team effort where you all pull together and you all do whatever. At the end, it has a very, very, very coming together aspect to it. When you start up a machine or start up a process and you get it to running, and at some point in time, everybody just kind of comes together and has a nice meal, and you enjoy the steak or whatever it is that you enjoy eating much more after you've started up something that you've made some accomplishment with. It really is a very popular, very nice thing. So again, I don't want to. We're out of time, but does anybody have any questions? We're not going to hit every one of these. We're just going to hit some of them. But I want you to know parts and pieces of this because they're very practical. This thing about the megger, that's a new megger. I didn't really know that that's what it was, but the old style meggers, you physically did this. I didn't do that. I would ask the electrician to say, "Have you meggered the motor yet?" They'll say, "Yes, I've meggered the motor." You know, "Yes, sir. Yes, master. I've done it, and we're ready to go." But until they've done that, you cannot start that motor up. You cannot start it up until you got that question answered and checked off. You cannot do that, or it'll blow up. It could, poof. So You do not want that to happen. Victor? See you next. By the way, Monday, the 27th, I'm not going to be here, so there will be an assignment of some kind, but